Our next speaker is Ernesto Vallejo, and we will talk on a diagrammatic approach to Kronecker squares.
I would like to thank the organizers for giving me the opportunity to talk here. I will speak about Kronecker coefficients, and this is the outline of the talk. First, I will give the definition, and then I will speak about an old method for computing Kronecker coefficients. It's 60 years old. I will explain you the method, and then go to what I think is an improvement on this method, and I call this a diagrammatic method. I will explain it, and then I will give two applications. One is to the Saxon conjecture. I will explain what is the Saxon conjecture. And the other is a new stability property for Kronecker coefficients. And the idea of the diagrammatic method is that you can use it to compute some Kronecker coefficients when one of the partitions has small depth. So it is useful for some computations, but it has also been useful to some more conceptual results. Let's start with three irreducible representations of the symmetric group, Sn. Then the Kronecker coefficient G lambda mu nu is by definition the multiplicity of the irreducible representation V nu in the tensor product of other two representations. So then if you have the tensor product, it's a representation of the symmetric group, and you can decompose it into irreducibles, and each irreducible appears with this multiplicity. So these numbers are non-negative integers, and we are interested in those non-negative integers. It is an open problem, very hard to find a combinatorial or geometric descriptions of the Kronecker coefficients, such as the existing ones, for example, for Koska numbers or Littlewood-Richardson coefficients. In fact, these numbers are much harder than Littlewood-Richardson coefficients. Now, there is an old method, as I told you before, goes back to 54 by Robinson and Tolby, and there has been some variations of it. For example, Littlewood in 56 give a variation, and another was done by Garcia and Remmel, and there are applications of these methods in some papers. Now, the Robinson-Tolby method uses the following ingredient. Given a composition, let phi pi denotes the character of the permutation representation. So this is the vector space generated by the left coset of the Young subgroup S pi associated to the partition. And the symmetric group acts on left cosets, and this action extends linearly to the whole vector space. Alternatively, you can think of the representation induced from the trivial representation of S pi to Sn. And with these permutation representations, we can do the following. Take the character of the irreducible representation V lambda, and then by the Jacobi-Trudy identity or determinant, you can express the irreducible character as an integral linear combination of permutation characters. And these numbers here are integers. It can be positive, 0, or negative. In fact, these numbers are the entries in the inverse Koska matrix. And then if we use this notation for the inner product of class functions, you have that the Kronecker coefficient is this inner product. And then if you expand chi nu as a linear combination of the permutation characters, you have by linearity this formula here. And the idea of Robinson and Tolby is that this number can be computed combinatorially. So, in other terms, you have the Kronecker coefficient is an alternating sum of combinatorial numbers. And I'm going to explain briefly these numbers. There are some technical things, so I'm going to try to avoid technicalities and only talk to you about ideas. So take partitions alpha, beta, lambda, mu, such that lambda minus alpha and mu minus beta, these two skew partitions, are of the same size, and then take a composition of this size. Then I define these numbers, LR, and we have these three parameters, two skew partitions and a composition. And this is by definition a multiple sum. You sum partitions, row 1 of pi n, of pi 1, up to partitions of row R of pi R. And these numbers here are generalized Littlewood-Richardson coefficients. Each of these is a product of Littlewood-Richardson coefficients. And the important thing is that this number can be computed combinatorially using Littlewood-Richardson coefficients. With this number, we have, using Littlewood-Richardson rule and Frobenius reciprocity, that this inner product is equal to this combinatorial number. In the previous slide, alpha and beta were empty, and these numbers were used to compute the Kronecker coefficient as an alternating sum. So this is essentially the Robinson-Tolby method, and I will use new ingredients to try to improve this method. The first one is the notion of spatial border strip tableau, or spatial ribbon tableau. I will not give the definition. It is enough to know that there are some things called spatial border strip tableau, or shape GNU. Of course, the entries are like border strips, and are spatial because they have to intersect the first column. And they have some notion of content and sign. The sign is essentially the same as the sign for the Murnaghan-Nakayama rule. But Important thing is that Elgesioglu and Remel show that for any two partitions gamma and nu, these numbers this number in the inverse Koska matrix has combinatorial description. Sum of signs of spatial border strip tableau, shape nu, and content gamma. So this is one of the ingredients I'm going to use. And then this definition I'm going to give you by example when two skew diagrams are isomorphic. They are isomorphic if there is a one-to-one correspondence between connected components of the skew diagram, and corresponding connected components are preferred by a translation on the plane. So for example, this component with three squares can be translated into this one, and this square can be translated into this one. So this is like a natural definition of isomorphic skew tableau. And then we come to the main new concept for the diagrammatic method. So given a partition lambda, we say that the skew diagram rho is lambda removable if there is a partition alpha such that rho is the complement of alpha. I will show in a moment some examples. But before I will make the following definition. So, take a diagram class D. By this I mean an isomorphism class of skew diagrams. And then R lambda D denotes the set of all lambda removable diagrams of the isomorphism type D. And by small r lambda D, we denote the cardinality of this set. So we collect in some sets lambda removable diagrams and we count them. And here is one example. Suppose lambda is this partition, then we have three ways of removing the square and having still a partition. So r lambda of the square is 3. Now take another diagram, take this diagram. This skew diagram has two components. One has 2 square, one has 1 square. And we have two ways of remove these from our partition diagrams. Now if you take this diagram here, we can remove in this way, but we cannot remove in this way because the complement is not a partition diagram. So in this case, the number is 1, and for this case, the number is 0. These are some examples of removable diagrams. Do you have some question about this? Then, when you have a diagram, a skew diagram that is not connected, you can express the number r lambda as some kind of polynomial in are lambdas of connected diagrams of smaller size. Here is one example, and here is another example. So, but here, for example, it appears this diagram that is not one of these, but it is like a composition, or I call it a collage of these two diagrams. And it's a general result. I'm not going to state it because I don't have time, but it's a general result that each time you have a diagram with several connected components, R lambda of this diagram is a polynomial in R lambdas of connected components. And I'm going to use this later in the applications. Now I'm going to give the formula of the diagrammatic method. So for each diagram class D, we make this definition. So what I am saying is that if you take this number here, this number is independent of the isomorphism class of sigma. So that's why this makes sense. And then, given a partition mu bar starting in u2, we define u tilde by adding in the first component another mu2. So this is a partition of D plus mu2. And then, if you take a spatial border strip tableau of shape mu bar, shape mu tilde, we will denote by tau of t certain permutation of the content of gamma t. This is just a technical point. This is essentially the content of t, but we need to arrange things in certain order. And tau bar of t is t2 up to tl. So we remove the first coordinate of tau t. And by et we denote the size of this t. Now, the result is the following. If you have a new bar, a partition of D, then for any n greater or equal than D plus mu2, and any partition lambda, there is this formula. Let's look at the left side. So the condition that n is greater or equal than D plus mu2 is just to say that this third component is a partition. Also note that here we have the two first components are equal. So we are talking about Kronecker squares, not general Kronecker coefficients. And the right-hand side has a sum over diagrams, the diagram classes of size at loss D, then some special border strip tableau of a shape that depends only on U bar. And we sum these products, the sign of T, L R D D tau T, and L lambda. First observe that this right-hand side does not depend on n. And it will depend on lambda, but in a nice way. Let's look at one concrete example of this formula. Take the partition mu bar equal to 1, and then I would like to compute this number, g lambda lambda n minus 3 to 1. Well, it equals this polynomial. It has r lambda for different 5 r lambdas for 5 connected diagrams. This is what the diagrammatic method gives you. So you can look at lambda. It can be very big, but you look at the border of lambda and you compute these removable diagrams when you have for any lambda this Kronecker coefficient. What I mean by a polynomial is the following. If you have C1 up to C5, our 5 diagrams, and xi is x of ci, we can write a polynomial, which is in 5 variables, which is this polynomial here. And by x4, I mean the corresponding variable to this diagram. And for example, 3x1 minus 4 is referring to this diagram and this factor, and so on. So then I can obtain from here really a polynomial in some variables, and the diagrammatic method is telling you that the Kronecker coefficient is obtained by evaluating this polynomial at different R lambdas. So in this sense, the method does not depend on lambda. What does not depend on lambda is the polynomial, but of course the evaluations depend on different lambdas. Okay? Then this is the general result. Given a partition U of D, then there exists a polynomial with rational coefficients in variables xc, one where C runs over the set of connected diagram classes of size at most D, such that for any n greater equal than equals to 2 and all partitions lambda of n, this Kronecker coefficient is obtained from the polynomial by evaluating each variable at r lambda c, as we did in the example. So this is the formula here in general. And now, well, this is the method, and I'm going to give. As you can see, you can use the method to compute Kronecker coefficients, Kronecker squares, when this partition has a small depth. So this is the computational part. And there are two conceptual or general.
This polynomial itself will not have positive coefficients, is that right?
No, not necessarily. No. They have rational coefficients, but the coefficients can be negative or positive. Yes. Okay, then I'm going to state the success conjecture. Take rho k be the node staircase partition. Then the success conjecture asserts that for all k greater or equal than 1, the Kronecker square V rho lambda tensor V rho lambda contains only reducible representations of the symmetric group. In some sense, Littlewood wrote in one paper a long time ago that this is the most complicated product to compute because it has many components you can do in small cases, and also the multiplicities tend to be bigger than in other products. So in this sense, this is more complex, and this conjecture was first studied by Pat Panova and myself last year, and Greta Panova will talk about this work in the next talk, so I will not say anything about these results. But I am given application of the success conjecture. For this, I need this notation. Let nu bar be a partition of V, and denote T of nu bar, the smallest k, such that this is a partition. So the size of rho k minus D, comma, nu bar is a partition. And also note C of nu bar, the maximum of D minus 1 and T of nu bar. Then with this notation, we have the following result. For each partition nu bar of D, there is a piecewise polynomial function with rational coefficients, S nu bar. This is defined on the real interval 0 to infinity, such that for any k greater or equal than T of nu, this Kronecker coefficient is obtained by evaluating S nu at k. So in other words, if you look at this Kronecker coefficient as a function of k, it is piecewise polynomial. And moreover, S nu is a polynomial function of degree D. D is the size of nu bar in the interval C of nu bar infinity. So this C I define here. And the leading coefficient is the number of standard Young tableau of shape nu bar. So in some sense, this polynomial has some combinatorial information inside. And here are some examples of polynomials for partitions of length at most 4. In these cases, C of nu bar is equal to T of nu bar, then this piecewise polynomial function is in fact polynomial. And what we would care is about the roots of this polynomial, because if you look here, when this is 0, then the Kronecker coefficient is 0, and we want positive Kronecker coefficients for the success conjecture. So the question is, where are the real roots of S nu bar? And in these examples, it turns out that they are all smaller than T of nu. T of nu is the range where it makes a meaning to talk about the Kronecker coefficient. And well, you have here those polynomials. So, and you can see in this case that the signs alternate. You have positive, negative, positive, negative, positive. So it's, I guess this should be a general behavior, but I have no idea how to prove that the signs alternate. And then An application of the previous table is that if you take a partition D between 1 and 5, a partition D of size at most 5, then all representations of this form are components of B rho K tensor B rho K. And another consequence of the previous result is that if you take any partition mu bar of D, then the Kronecker coefficient here will be positive for all K greater or equal than T of mu bar, with a possible exception of at most 2D minus some number values. So then this is the best approximation we can get now of the success conjecture. That given if mu bar is fixed and we let K grow, then only a finite number, at most a finite number of values would be zero, and the rest are positive. And of course, there is a conjecture which is equivalent to the success conjecture, and the conjecture is that the map S mu bar is positive in the whole interval, for it has some meaning to compute the Kronecker coefficient. And now to conclude, I will talk about the second application. For this, I will extend a diagrammatic method to arbitrary Kronecker coefficients. Now we need to take two partitions of the same size and two diagram classes of the same size. And instead of working with this R lambda D, we define now this set, which are pairs of removable diagrams. Rho is lambda removable of isomorphism type D. Sigma is mu removable in the class E. And the extra condition is that the complements of rho in lambda and sigma of mu are equal, are the same partition. And then we take this, the cardinality of the set. And with this, we can get a similar formula, the same hypothesis as before. And now the general Kronecker coefficient is this sum. And the only difference is that now we are summing over pairs of the diagram classes D and D. The sum of D is the same. And here, instead of having D, we have DE and this new number. And with this thing, we can obtain this new stability property. So given any partition mu, and any I and any K, let's denote mu ik this sum. This means you add K to the first I rows of mu. And then, in this case, given lambda, mu, and mu, then there exists a number m such that the map that depends on K, G lambda I of K, mu I of K, mu 1 chi A, is constant in this interval. This means this Kronecker coefficient stabilizes. The first component, what you do to the first two components, we add the K to the first I row. And the last component, you add Ki to the first row. And when I is equal to 1, this is the well-known Murnaghan's stability property. So, and this is something more general. And let me observe that this theorem was originally proved for the case lambda equal mu. This is what you can see in the extended abstract. And then this year, generalizations were found for any lambda and any mu by myself, and independently Pak and Panova have another formula for this general stability. And to conclude, let me give you, here is another example of a diagrammatic formula. You see that as the depth of mu grows, you have more connected diagrams of size D. This grows very fast, and then you see how complicated it is to evaluate a Kronecker coefficient. But you can see from this expression that the stability is something very natural, because if you have row, let's say row I and row I plus 1, and you grow row I long enough, then each of these numbers will not change as you grow the difference between row I and row I plus 1, because there will be no space for these numbers to change. These numbers will change only when the difference between rho I and well, between the lambda I and lambda I plus 1 are small. So for example, if they are 1, 2, but if they are 3 or bigger, then do not change. So this is like the utility of this, or this is how I got the idea of the stability condition by looking at these formulas. Okay? Well, thank you very much.
Some questions?
So what's the intuition behind the Saxel conjecture? So why, in particular, the staircase shape and its tensor square as opposed to, say, the largest?
Well, you see, at least the staircase shape is self-conjugate.
Yeah.
And then, in order to have the alternative, the partition 1 to the n, you need to have something self-conjugate. And in order to have the partition n, you need to have them equal. So then at least you need to have that you have a partition that is self-conjugate. And if you look at some examples, when you move to the middle in the lattice of partitions, it tends to be more partitions when you take products in the middle. So it is natural to look at some partition that is in the middle of the partition lattice. And rho k is 1. There are some conjectures about other self-conjugate partitions that are in the middle.
Any others? Okay, let's thank the